Which machine learning model should you use? You have looked into literature, there are a lot of models, and you are trying to see which model should you use for your problem. In this video, we will explain all these models: decision trees, random forests, boosting, support vector machines, key nearest neighbors, neural networks, and Gaussian processes. And by the end of it, we will also show you a roadmap to make this decision simpler. Let's start with how does Zeckhouser play bridge? First things first, what is bridge? Bridge is a card game involving elementary probabilities and statistics, knowing the behavior of your partner, and accepting that good decisions can actually lead to bad outcomes. Who was Richard Zeckhouser? Richard Zeckhouser was actually bridge champion, 40 years apart. Okay, very interesting. And he is also professor of behavioral finance in Harvard, which is a field, behavioral finance, that demands the use of probabilities. Okay, like um, like machine learning. And how does he play bridge? He plays by drawing the decision tree in his mind and attaching a probability to every possible decision. That is not a card game trick, it is actually a machine learning algorithm. Before we go, we can actually explore where I saw this. I first saw this in the investment letters from Sleep and Zakaria, Nick Sleep, okay, and in Poor Charlie's Almanac from Charlie Munger. So let's just check this really fast. And in those letters they described this. In one of Charlie Munger's talks, he makes the statement, the right way to think is the way Zeckhouser plays bridge. It's just that simple. Well, to a young man in London, that is the very infuriating statement, as it took me about a year to track down who Richard Zeckhouser was. He was world bridge champion in '66 and, among other things, now runs a brilliant behavioral finance course at the Kennedy School of Government at Harvard. So, how does he play bridge? He thinks via decision trees and attaches probabilities to the various branches. And as the facts change, he changes the probabilities. The book that I first read with this was this. I actually preferred the the blue cover, okay, of Poor Charlie's Almanac, which I recommend, of Charles T. Munger. And let's continue. So let's go here to the decision trees. The question is, what are decision trees? Decision trees, they work by taking all the data that you have, all the examples, and then divide into these smaller branches. Imagine this was um, a molecule that cured a disease, and this was the positive class, and here then this class 2, it didn't cure a certain disease. So the group of molecules cured the diseases, and here the group of molecules didn't cure the disease. Let's say it like this. So the molar mass, if you divided those with higher molar masses and then with lots of hydrogen bonds, then you arrive at class 1. And then if you divide the ones with low molar mass but high polar volume, you will arrive at also the class 1, but for different reasons. For example, you can have two molecules doing the same thing, but for different reasons. And this is where decision trees excels, this idea, and explains very well why machine learning works in terms of not only using linear regression, which is the same reason for every compound, for example. The idea is that one question at a time. Each split, okay, divides the data into two smaller groups, poorer groups, and you keep going until a group is poor enough. Okay, poor enough means that you have restricted that group to the same conditions, okay, to the same decisions. Why it matters? Because different branches can reach the same class for completely different reasons. So you can read the whole model out loud to explain it. Almost no other model can do this. You simpler models like this are linear regression, okay, uh, logistic regression. You can also have rules to explain this, but not like the other complex methods, other complex models. They are not as simpler as decision trees. Okay, and this is the advantage of decision trees. What is the problem? Is that one tree it memorizes and 1,000 trees generalize. You will see how. So if you grow a tree deep enough, and it will split every training point until every training point sits on its leaf, on its own leaf. It's perfect on the data the model already knows, but useless on data unseen by the model. So how can we fix this? Let's see. Bagging. What is bagging? We build many trees and then we do a final voting. How do we build these trees? We divide this data set in smaller, the training set in smaller parts and do these trees and fit these trees to these smaller parts. Then we have several models and we average the final prediction. Okay, the prediction is the average that you obtained. So this is called bootstrapping. You draw random samples with replacement. Okay, every model sees a slightly different part of the data. And this is good then to generalize, okay, not to overfit. You train in parallel, you have n models, none of them aware the others exist, and it's good also for parallelization really computationally. And then you combine, use the majority vote for classification and the average for regression. Random forests, it's bagging that you just saw, but with one twist. Which twist is this? The twist is that each split is only allowed to look at a random subset of the features, not only a random subset of the rows. Bagging is sample bagging. You look at a random subset of the training set in terms of number of examples, but in random forests, each tree also takes into account a subset of all the features, okay, a different subset. Why it matters? Because without this, every tree grabs the same dominant descriptor first, and they all come out near identical. This way, you will have really different trees, different results, and the average will result in less of overfitting, and it matters better predictions. So, random forests can be defined as ensembles of independent decision trees trained with sample bagging and random feature subsample, like feature bagging, let's say. It's hard to beat random forests because they are fast, they barely need tuning, and it tells you you have the entropy, the Gini-based entropy, which tells which features matter most for random forests. So it's a really good method, okay, when you want to have a good result without a lot of fitting, without a lot of tuning. Another type of method based on decision trees, it's boosting, which it's basically you build decision trees in sequence. You take the original training data, you do a decision trees. If you have examples correctly classified, they are correctly classified. Okay, cool. And then you take those misclassified and you fit another tree. And again, if you have those correctly classified, very nice. You take the misclassified and run another tree. Okay. and so on and so on and so on. So the idea is the subsequent model is trained on what the previous model got wrong. This model trained on what the previous model got wrong. The trade, okay, there's a trade here. Usually the most accurate model you can use, it's the most accurate model you can use for tabular data, like Excel kind of data with numerical rows. But also it's the easiest to overfit, okay? You, like in decision trees, if you go on and on and on, you start overfitting. You keep boosting and it will learn your noise, okay? You'll start to learn what is actually noise. It's sequential, so it doesn't parallelize like a random forest does. Okay, it's not as efficient from the point of view of computations. These are some of the most well-known algorithms, models: XGBoost, CatBoost, and Light GBM. If you have these like championships or comparison of the best models, okay, these ones appear at the very top, okay? And then you find random forests over there and some really large neural networks models, okay, pre-built models. But these are very good models, okay? Like 10 years ago, random forests, when in those data science competitions, it beat everything, and in the last 10 years, XGBoost and then CatBoost and Light GBM beat obtained the best models. Support vector machines. In support vector machines, you have many lines that separate, for example, two different classes, and support vector machines picks the one with the most empty space of either side, tries to maximize this space. The points touching this margin are called the support vectors. So you have the support vectors as fast as possible from the hyperplane. Here, instead of only having one line, you actually have a plane, okay, dividing this data, and you try for it to have the widest margin. Imagine that you cannot separate these two classes. Then it has a very cool trick, the kernel trick, where you increase another dimension, like you put, for example, consider another property or another row, you increase another dimension. When nothing works, it lifts the data one dimension, and then you can separate the two classes, okay? And this is how it works. It's strong in high dimensions when you have many features on small datasets. It's slow to train once you pass a few tens of thousands of rows. Okay, this is the trade-off. K-nearest neighbors, also very popular. The model that isn't one. We will see why it isn't really one model. Okay. So you try to guess the movie popularity, and you have as columns the actors, famous actors, and IMDb rating. What it does is, when you have a new movie coming in, it calculates the Euclidean distances in terms of these properties with the other movies, and see if it fits the popular class or the unpopular. So the idea is that there is no training. You store the whole data set, and when your new pointer writes, it tries to find the closest neighbors in terms of Euclidean distance and copy whatever most of them are, like the class or the property, the outcome that you are trying to define. So training costs nothing. Prediction costs everything. Every new point is compared against the old dataset, and closest does not mean much in higher dimensions. At high dimensions is something that doesn't work very well, okay, when you start having many properties, many features. Now the almighty popular artificial neural networks, okay? You'll have here a neural network. You have the input layer, you have the output layer, the thing you are trying to predict, and the hidden layer, which is where all the secret sauce lies. For the hidden layer, you can define a nonlinear activation function, okay? And the method, the model will optimize these weights in the function. So the inputs are the number of features, the descriptors, and for example, if you have 10, 20 descriptors, features, you will have in the input layer 10, 20 nodes. In the outputs, you have one node for regression because it tries to guess only one value, two or more for each class in classification. Binary classification, you have two nodes. Trinary classification, you have three nodes, for example. Each connection between the neurons has a weight, and the weight controls how strongly one neuron influences the next. And in this way, we can say that is inspired on the human brain, but I also heard that it was not inspired on the human brain, so let's leave it at that. It uses the method backpropagation to see how much each weight contributed to the final error and therefore optimize these weights. Okay. The secret sauce, like I said, it's the hidden layer, and you can make this hidden layer very, very complex, okay, and fit almost everything. So the price is, it needs a large data set before it beats a boosted tree. It has real computational effort, especially as the number of nodes increase. Okay, so that's it. Gaussian processes, predictions with uncertainty. The other methods, you can have uncertainty, usually if you run it many times or if you know how the inputs can vary, okay? But Gaussian processes, they really have you really have a way to obtain uncertainty. So you start with a few known data points, okay? Uh, you fit many smooth functions, Gaussian functions, over your data. When you are closer to the data points, you have a lower error, and here, when you are away from the data points, you have a larger error. And this results by fitting all these functions. This is a result of all the functions, okay? So, near the points, a lower error, away from the points, a larger uncertainty. Why would you want this? Every other model here hands you a number and no indication of whether to trust it or not. Whereas a Gaussian process, it returns a distribution, a prediction, plus an error bar that widens automatically whenever you have no data. Okay, so you have the x, okay, that you are trying to predict, what you're trying, and then not only a value but the distribution. Okay, when you make a prediction. The caveat is that it's best for small data sets. The computational cost grows roughly with the cube of the number of samples. Okay, it has a very high cost with the number of samples. So let's go. How do you choose which machine learning model to use? First, you see if you need uncertainties. You can use this flowchart, okay? Do you need uncertainties? If yes, use a Gaussian process. It's the best process to obtain predictions with uncertainties. If not, first try linear regression. If it's accurate enough, you have a simpler linear regression problem, okay? Where your output varies linearly with your inputs, and you should stop right here. If not, you see, do I have more than 10,000 samples, then go for neural networks, in particular deep learning. Make this very large neural network. If not, you are better served off using random forests and gradient boosting. Okay, performs very well on tabular data, or support vector machines if you have few samples but a lot of dimensions. Okay, a lot of features. And this is it. You can use this flowchart to help you decide. So, one page cheat sheet. Let's see the advantages and what watch out for every model. Decision trees. You use it when you need to explain the model to a human, but be careful because it overfits alone, and it can be unstable when you have more features than samples. Random forest. Default. It can be your default. It should be your default first on tabular data because it's very easy to fit, and you usually have good results. Or it approximates very well the best results. It loses readability, the readability of using only one tree. Gradient boosting, you use it when you want maximum accuracy, especially for tabular data, but it overfits if you are not careful. Okay, and it's sequential, so it doesn't parallelize computationally as good as random forests. Support vector machines. It has many features, few samples, and it's slow on large data sets. Use it for when you have many features and few samples. K-nearest neighbors. You use it when you need a baseline in like 5 minutes. It's slow at prediction and fails at high dimensions. Baseline, like the minimum accuracy that you can have. Neural networks. You use it when you have more than 10,000 samples and complex relationships. You must be careful with because it needs a lot of data and it may be difficult to explain, but there are ways to do this, and we will see this. Gaussian processes, you use it when you need an honest error bar, but be careful with its computational cost. It's the cubic of the number of samples, and then it makes it only useful for small data. So, if you have a question, leave us a comment, okay? Or if you have a topic that we want us to do a video on, and let's go for the next topic and the next video.